different method where we don't just learn tricks but system and processes that will enable your children to have a very good foundation in mathematics. So we want to look at one of the foundation block of fundamental arithmetic, and that is prime numbers. So these are numbers greater than 1, but that's two factors which are just 1 and itself. So example of those numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 43, 47, 53, and so on and so forth. So this prime number is very, very useful, and we'll be using it as our basis for some of the few episodes that will be coming after this. So with these prime numbers, we can do something. We can say they can ask us to express something as a product of the prime factor. So let's pick this example. Express 60 as a product of prime factor. So you continue to use the prime numbers until we get to the bottom that everything it remains 1. So that's how to express as a product of prime factor. So we're given 60 now. So let's practice this. 60. So if you look at the prime numbers, you see the first number that will go in 60 completely is 2. So let's have 2 in 60. That's what? That's 30. What could go again? 2 could still do. 2 could still do. 30. 2 in 30. That's 15. Yeah, 15. If you look at it now, 2 cannot do again because there is going to be a remainder. So we move to number 3. So 3 we do with 15. So 15 divided by 3, that's 5. And 5 being a prime, 5 we divide 5. So 60 as a product of prime factors will now be equals to 2 times 2 times 3 times 5. So that is a 60 as a product of prime factors. I hope you get that. You can practice 84. So we look at LCM. LCM simply means the lowest common multiple. So let's consider this question. Find the lowest common multiples of 1, 8, 10, and 12. Then 2, 12, 15, and 18. So let's look at 8, 10, and 12. So from the knowledge of the prime numbers, we are going to use prime numbers to divide all through. And anywhere we get to, if you cannot go in it directly, we'll repeat the number. So let's try 8, 10, and 12. So the first number that we'll see that will go there is what? Is 2. Looking at prime numbers. So 8 divided by 2 will give us 4. 10 divided by 2 will give us 5. You can see 6 2's in 12. So if you look at 4, 5, and 6, you see that 2 could still do. So we must finish up with one number before we move to the other number. So let's go with 2. 2 and 4 will give us 2. 5 divided by 2 is not possible because 5 is odd while 2 is even. So we repeat those 5. Then 6 divided by 2 will give us 3. So if you look at it, 2 will still work because we still have one remaining 2. So 2 in this one. So 2 divided by 2 will give us 1. 5 divided by 2 again is not possible. So we repeat the number. Anytime it does not go, you repeat the number. And 2 and 3, the same thing should not go. You repeat the number. So let's go to the next number. We have 1, 5, 3. So 3 is the next one we pick. So 3. So we have 3. So this one is already solved. So this will remain 5 as well because 3 cannot divide 5 completely without any remainder. So 3 divided by 3 will give us 1. So we are left with 5. So 5. So that is going to be 1. And 5 divided by 5 will give us 1 and another 1. So the LCM of 8, 10, and 12 will be 2 times 2 times 2 times 3 times 5. So if you multiply 2 times 2 will give us 4. 4 times 2 will give us 8. 4 times 3 will give us 8 times 3 will give us 24. And 24 times 12 will give us 120. So the LCM of 8, 10, and 12 is 120. You can practice this by yourself. Application of a prime number. So you go to highest common factor. It's called HCF in short. So let's consider this question. Find the highest common factor of 24 and 40, and the second one 60 and 108. So the same method we use finding our LCM. The only difference between finding the LCM and HCF is that in HCF, you make sure that the factors, the prime numbers you are going to use must be common to the numbers that are given. So let's practice this. Let's practice. So 24 and 40. If you rewind and look at the prime number, you see that 2 will go in 24 and 2 will also go in 40. So let's start with 2. So 2, that's 12, and 40 divided by 2, that's 20. Remember, the factor must be common to the number that are given. So 2 will still do here. So we have 2 again, 2 again. So 2 in 12, that's 6, and 2 in 20, that's what? That's 10. 2 will still do again. 2 will still do again. So 2 in 6, that's 3, and 2 in 10, that's 5. If you look at this two last number, there is no factor that is common to both 3 and 5. So whenever you get to the numbers that their factors are not common, you stop. That's your HCF. So the HCF for this one will be equals to 2 times 2 times 2 times 2. And what will that give you? 8. So let's look at 60 and 108. If you look at it properly, you see that 2 will go in both 60 and 108. So 60 divided by 2 will give us 30, and 108 divided by 2 will give us 54. So if you look at 30 and 54, 2 can still do it. So we have 2 in this one. 30 divided by 2 will give us 15, and 54 divided by 2 will give us 27. So if you look at 15 and 27, 2 has finished his own business. So we move to number 3. Let's look if 3 will go in both of them. So 15 by 3 will give us 5, and 27 by 3 will give us 9. I told you before, your multiplication table must be your partner when you are dealing with mathematics. So 3 will do. So 15 divided by 3 will give us 5, and 27 divided by 3 will give us 9. There is no common factor that will divide both 5 and 9 completely. So when there is no common factor again, that is where you are going to stop. That means our HCF for 60 and 108 will be equals to 2 times 2 times 3. And if you multiply that, 2 times 2, 4, 4 times 3 will give us 12. So that's the HCF of 60 and 108. Subscribe to Basic Math Hub at YouTube. Prime numbers. Let's consider this question. Find the greatest number which will divide 140 and 80 without any remainder. What are they asking us to find? Just the highest common factor. That number that will divide 140 and 80 completely without any remainder is the highest common factor. So we find the highest common factor of 140 and 80. These are the applications of the prime number. So we start with the prime numbers, the prime factors. The first one we can see in this place is 2, because any number that ends with 0, 2 will do the justice to dividing it. So that's 70, and this is 40. So 2 will still go. 2, that is in 70, that's 35, and in 40, that is what? That is 20. So what can go now? 2 cannot go again. If you observe 3 will not go as well. 3 cannot go in 35, can also not go in 20. So at the 5 will go. So 5. So we have this one will give us 7, and this one will give us 4. So if you look at it now, there is no other prime, no other number, no other common factor that could divide both 7 and 4 without any remainder. So our HCF is 2, and what? And 5. So that means the number that will divide 140 and 80 completely is going to be 2, and 5, and that will give us what? 20. And if you observe very well, it's only 20, the highest number that could divide both 140 and 80. So that's one of the applications of the prime numbers. See you in the next episode. Subscribe to Basic Math Hub. Let's consider this question. It's a Becker question. What's the difference between the LCM and HCF of 12, 15, and 21? So we are looking for the LCM. We look for the HCF for the same number, and then we do what? We subtract. So let's do the LCM here. So that's 12, 15, and 21. So for the LCM, we have it in mind. We divide through until everything remains 1. So 2 comes to our mind because of 12. That's going to be 6. We'll repeat this, and we're going to repeat this. That's 2 again. 3. We'll repeat this because it cannot go completely, and we'll repeat this. Then we go to 3. 3 will do now. So 3 we have 1, we have a 5, and we have a 7. So 5 we do now, 5, so we have 1, and we have 7. Then 7 now, we have 1, 1, 1. So our LCM is going to be 2 times 2 times 3 times 5 times 7. So let's multiply through. 2 times 2, 4. 4 times 3, 12. 12 times 5, 16. And 16 times 7 will give us 420. So the same number we are looking for the HCF 12, 15, and 21. So what's the common factor of 12, 15, and 21? Look at it. 2 is nowhere to be found. But 3. Let's look at 3. 3 is good. So 4, 3, that's 5. And this one, that's what? That's 7. Do we find any other common factor again? No. So that means the HCF is equals to what? Equals to 3. So therefore, the difference between the HCF and LCM is going to be 420 minus 3. Simply, our answer is going to be 417. Hope you get that. Subscribe to Busy Mathematics. So let's consider this question. It's also a paper question. Find the LCM of 9AB, 18B squared, and 3AB. 9AB, 18B squared, and 3AB. I will suggest to you to first deal with the numbers first, then we'll go to the algebraic letters. So here we have our LCM. The numbers, if you look at this very, very keenly, you see that 2 because of this 18. So that's 9AB. We are repeating others. 9B squared, repeating others, and 3AB. So let's deal with the numbers now. So 3, let's continue. 3, so that's 3AB, and this is 3B squared, and this is going to be AB. So 3 could still do here, so that's 3. So we have AB, we have B squared, and we have AB. If you look at it now, we see B, or true, B, so that's going to be A, that's going to be B, and that's going to be A. So what next? Or A now. A, so that's going to be 1, that's going to be B, and that's going to be 1. So our B again now. So that's 1, 1, 1. So our LCM is going to be 2 times 3 times 3 times B times A times B. So let's multiply through. 2 times 3, 6. 6 times 3, 18. 18. How many here do we have there? A. And how many B? B. That's B squared. So find the HCF of 24PQ and 16P squared. 24PQ and 16P squared. So don't forget that when you are dealing with HCF, the factors you are going to use, the prime numbers you are going to use must be the common factor of both numbers. So I suggest we deal with the numbers first. So let's take into cognizance 24 and 16. So 24, 2 we do, so that we have 12. Our PQ remain, we have 8P squared. So the numbers again, 2 we do, that's going to be 6PQ and 4P squared. 2 we go again, so that's 3PQ and 2P squared. So let's look at the alphabet keenly now. You see what is common? P is common. So we have P, that's going to be 3Q, and we're going to have 2P. So 3Q and 2P, there is nothing common with them again. So that means our HCF is here. So that's going to be 2 times 2 times 2 times P. So let's multiply through. 2 times 2, 4. 4 times 2, 8. And 8 times P will give us 8P. So the HCF of a 24PQ and 16P squared is going to be 8P. Hope you get that. Subscribe to Basic Solid Foundation in Mathematics. So factorize 9PS minus 24PY. So we are still coming using the knowledge of our prime numbers, HCF, and the rest. So what you're going to do in this kind of question is use what we call the common factor method. The common factor method. So the common factor method is the most easiest way to factorize. So the common factor method is like looking for the HCF. So we have 9px then 24py. So HCF now, what can go in 9 and also in 24? Let's pick the numbers first. So we see 3 we do, so that's going to be 3px, 3ps, and 8py. So for the numbers, there is nothing again. So let's look at the alphabet keenly. So we see p, so we have p, it will remain 3x, and we have 8y. So for factorization, our HCF is going to be our multiplier staying outside the bracket, while the remnant, the last one where we stop, is going to be inside the bracket. And we should not forget the sign as well. So what should we do now? 3 times 2 will give us what? 3p. So we open our bracket. So what do we have here? We have 3x. What's our sign? That's minus, and that's what? 8y. That's the simplest way for a child to have a solid foundation in mathematics. Let's consider this question. Find the smallest number that can multiply 24 to make it a perfect square. So we are still applying our prime numbers. So we're going to have 24. So we keep multiplying, we keep dividing by the prime number. So 2, though that's going to be 12. 2, that's going to be 6. 2, that's going to be 3. And lastly 3, that's going to be 1. So let's group it now in indexes. So 2 raised to power 2 times another 2 raised to power 1 times 3 raised to power 1. Before anything can be a perfect square, it must be raised to the what? To the power of 2. It means for 24, before it could become a perfect square, we need another 2 and we need another 3. So that means to make 24 a perfect square, we need 2 times what? Times 3, which is equals to 6. And if you check very well, 6 times 24 will give us 144. And 144 is a perfect square because the square root of 144 to have a solid foundation in mathematics. Now let's look at this, and we will find the square root of 1225. Still using our prime knowledge. So if you look at this, any number that ends in 5, we divide it without any remainder. So let's consider it. It's not possible in 1, but in 12, we're going to have 2. That's 12. That's 10. It remains 2. So in 22, that's 4. That's 24. It still remains 2. And in 25, that's 5. So 5 we still do by virtue of being handy. 5 in 24, that's going to be 4. And in 45, that's going to be 9. So what do we have now? We have in 49, we have 7. 7 we divide 49, that's 7. And 7, that's going to be what? Be 1. So the square root, we are going to get it by grouping into 2, the same number. So we have 5 raised to power 2 times 7 raised to power 2. So the square root, so it's going to be 5 times 7, which is equals to 35. Do you get that? That's the best way possible without use of calculator to get the square root of big numbers. See you.